All right, back from the break. That may have been a short break or a longer break. In any case, we've got 4 new problems to look at, so let's get started and see what these problems are all about. It looks like the first one is from relativity. Now, just as a comparison, in the last practice midterm, that relativity problem was from energy and momentum calculations, energy, momentum, kinetic energy, velocity. This one actually is with time dilation and length contraction. So both of those could be the types of problems that could show up. Now the early part of chapter 26, I always suggest to students, you can read those early sections in 36, that's fine, that describe some of the history behind the development of relativity, but it's not really going to show up in the examples that we're looking at. The examples we're looking at are kind of oriented towards practical application of the formulas, so we need to be able to go in and calculate length contraction. I'm going to say length contraction, time dilation, velocity addition, and then pretty much everything we looked at in terms of energy, momentum, kinetic energy, and velocities. So what are all the new rules for how those are going to work? All right, so here is the spacecraft. Let's take a look at setting up the problem because that's really important. It says we've got a spacecraft traveling to a planet. The planet is 10 light years away, so it's actually a pretty nearby planet, right? It's one of the nearby star systems. And it says that we want to plan the trip so that it will take 5 years for the people in the spacecraft. So, 5 years out, maybe they spend the weekend, get to know everybody at the other planet, 5 years back. So 10 years is going to pass for them. Let's see how much time passes on Earth. Now, the first thing they ask us about here is, for the numbers given, what's the speed at which the spacecraft would have to be traveling? So let's get the 2 reference systems set up. So here's our diagram. So on the left, I'm saying there's a certain distance. I've labeled that as L. And L is given. L is given as 10 light years. Now we've seen these examples before with the spacecraft examples, long distance examples, and the units, writing light years as c times years really helps. So I'm going to do that. I'm not going to convert this, I'm not going to spend time converting this into meters or something like that. I'm going to leave it as light years, but I'm going to write it specifically as a factor of c times years, and then a factor of c can be canceled if we need to. So let's take a look and see how this works. So what we're told is that in this reference frame on the left, which is the reference frame of the planet and the Earth, there's 10 light years of separation. Now we know that when we move into the reference frame of the spacecraft, the spacecraft is going to observe the Earth and the planet both in motion, and that means that the distance between them will be shortened. So the spacecraft is looking into another reference frame. All of those distances in that other reference frame are going to be shortened by a factor of gamma. So what we can write down is that L prime, the length in this other reference frame, is going to be L divided by the gamma factor. Now, they have not told us what L prime is, so I don't have that to use. I know the length in one of the reference frames, but I don't know it in the other. Now, they've told us the time, but they've told us the time in the spacecraft frame. So I'm kind of stuck here in that the distance is given in one of the reference frames, but the time interval is given in the other reference frame. They don't go together. If I knew t and L in the same reference frame, I could solve for velocity, but I can't do it yet. So I'm going to have to think a little more carefully about the formulas. Now, if I look in the reference frame of the spacecraft, there's t prime T prime is given by L prime over V, and I know that L prime is L over gamma. So I've written a formula over here, the L over gamma V, where I know what L is, and I know what T prime is. So using this formula, I can then solve and say that gamma V is equal to L over T prime, and L is 10 light years, and T prime is 5 years. So the years will cancel out, but I keep the factor of C, and that says that gamma times V needs to equal 2 times C. Now I think in class, in the lectures, we mentioned that when I get formulas with gamma V in them, the way to solve this is either rewrite the V in terms of gamma or rewrite the gamma in terms of V. Now, I always write the V in terms of gamma. Almost always that leads to an easier calculation, so I'm going to go ahead and do that. Often students choose the opposite, and that's because gamma is not nearly as familiar, but it is going to, in these cases, typically make the calculation easier. So I'm going to take gamma times V is equal to gamma, that's my gamma factor, and then for V I'm going to write 1 minus 1 over gamma squared to the half times C, and then I'm going to multiply through by that gamma, and gamma times V is the same thing as gamma squared minus 1 square root times C. So I took that expression and set it equal to 2C, and then what that's telling me is that gamma squared minus 1 should be 2 squared, also known as 4. And then when I add the 1 on, gamma should be equal to the square root of 5. Okay, so I did have to step through that carefully and make sure that I got the L from reference frame 1 and the T from reference frame 2. I needed to put together the formulas in a way where I could use both of those pieces of information, and we did it. And so now I've got the gamma factor, which is going to be able to tell us the speeds that we're going to have to use as a relative speed between the reference frames. And so the gamma factor, 5 square root, is 2.236. Solving for V, that gave 0.894. So these astronauts, they're going to head out for 5 years, and then they're going to spend the weekend, they're going to come back they're going to spend 10 years in this spacecraft. They're going to need to travel at 89% of the speed of light, which is really, really fast. We're going to have to really get them up to a high speed, and it's still going to take 10 years to get out there and back. So in part B, they say, okay, fine, if it's 10 light years in reference frame 1, what's going to happen in reference frame 2? And now we can just use the length contraction formulas. These are kind of like puzzles, and then once we get that velocity solved and the gamma factor, everything else should kind of fall into place. So we can, pay attention and make sure that we're getting sensible numbers for this. So I ended up with an L prime 4.47 light years. Now that makes sense because it's only taking us 5 years to get there. And so it's going to have to be shorter than 5 light years, and it turns out it's 4.47. Now how much time is going to take place on Earth while the astronauts are gone? And it's going to be 11.2 years during the time the astronauts are traveling out to the other planet. So during that 5-year interval on the spacecraft, 11.2 years transpire on Earth. So let's see, astronauts 5 years out, spend the weekend, come back 5 more years, that's 10 years plus a couple of days. And back on Earth, meanwhile, 11.2 plus an additional 11.2, that's going to be 22.4 years. So 22 years have gone by on Earth and 10 years have gone by on the spacecraft. So coming back, everybody's going to be 12 years older. All the age differences will be shifted by 12 years. Everybody's going to be 22 years older, but the people in the spacecraft will only be 10 years older. All right, Now, in part D, they say during this travel, the spacecraft is going to be using radio communication with Earth, and it's going to be using a wavelength of 10 meters. So this 10-meter radio signal is going to be Doppler shifted. So we can use the Doppler shift formulas. Now, on the way out, as the spacecraft and the Earth communicate using this 10-meter wavelength, everything is going to be redshifted. And by redshifted, we mean that it's going to be shifted to longer wavelengths. So the people back on Earth receiving the signals and the people in the spacecraft receiving the signals as they communicate using 10-meter signal that's being sent out, they're going to have to listen for that signal at 42.3 meters. So the redshift factor, based on the velocities that we calculated here, are going to be 4.23. Okay. So Earth and the spacecraft are both sending out signals at 10 meters, but they're both listening for the signals. They're both got the antennas listening for something coming in at a wavelength of 42.3. Now, on the way back, it's going to be blue shifted. And so this time, we've got to flip the velocity directions in our Doppler formula, and that's giving us the inverse of 4.23. It's giving us 0.236. So on the way back, we're going to have to be listening at 2.36 meters for the wavelength. We should have written in frequencies, I guess. I didn't do the frequencies here, but you could be asked that. So you could be asked about frequencies as well as wavelengths involved with these Doppler shifts, or energy. Energy is kind of the fundamental unit here for these photons. So any questions, let me know. Stop by office hours and we can take a look. Again, the key here is being really clear about the two references and taking the distances and the times and making sure that you've placed them into the correct references. All right, let's move on to problem 2. Now, problem 2 here is, I guess I better go back and look at it. Problem 2 says, let's imagine that nature is somehow different. That instead of the electrons having masses of 511 eV, 1000 eV, they only have masses of 100 keV. So the electron is 1/5, a little less than 1/5 of the mass. Now, we don't know why electrons or protons have the masses that they have, but if we start fiddling around with the masses, maybe some of the formulas will change. We could go in and find out what kind of predictions we could make if, we went to a different universe, a different cosmos, where the electron had a different mass, or the proton had a different mass. How would it be different? So the protons in this universe, in this cosmos, have a mass of 1800. Now that's quite a bit lower than what masses we have here. So in this universe, the proton masses are much higher than this. They're 1,000 times higher than this. So this is going to make a big difference. This is a huge reduction, or 500 times less, let's say. This is going to be, pretty close to 500 times less. This is going to be a pretty significant reduction for the mass of the proton. So how's that going to change things? Now, all the other physical constants we're going to say are kept the same. Gravity works the same way. Electric forces work the same way. It says find the 4 lowest energy states of hydrogen and then start calculating energy and wavelengths of photons that would be generated in electron transitions in hydrogen. So, all right, here is our hydrogen atom. We went through the Bohr model. So the Bohr model, we said, was incorrect, but somehow it gave us the right formulas for energy. Now we're going to be coming back in chapter 39 and getting the right formulas the right way using quantum mechanics. But for now, we're kind of left with just using the correct formulas that were developed using the wrong assumptions. All right, so here's the formula. that we had developed. Now, in this problem, I actually introduced alpha. Alpha is known as the fine structure constant. It's written in your textbook. The textbook talks about this. Another way of thinking about alpha is it's kind of a quantum version of the electric magnetic force constant. So the electric magnetic force constant, little k, times the charge of the electron and the proton squared, divided by Planck's constant, divided by 2 pi, times the speed of light. If we take that particular set of physical constants and combine them, this combination is unitless. Now, physicists really like that because you might say this. You might say, look, little k, is that a big number or a small number? Is the electric force a really big number or is the electric force constant really small? And you go, well, there's no way to tell because it depends on what units we're using. The electric force constant that we've used through Physics 4b, that depended on units. It depended on how we defined coulombs and how we defined kilograms, how we defined meters and seconds. All those units are combined into the electric force constant. Now, by multiplying by these other factors, and instead of using little k, using alpha, alpha doesn't have any units. So we can now definitively say that the electric force is that strong. It's 1 over 137. Okay. Now, it's not 1 over 137 exactly. It turns out that the electric force constant, the quantum version of the electric force constant is unitless, and it tells us how strong this force is. You can actually do the same thing with all the force constants. You can take the gravitational force constant and multiply it by factors of c and h bar and such, and turn it into something that's unitless. I guess you have to define a mass for that. Maybe, maybe not. And then you can also take the strong and the weak forces of nature. You can take all the forces and rewrite them in terms of unitless numbers. And that actually allows us to tell how strong are these forces, independent of the way we've defined units. Okay, so anyway, it means that we can take this formula, which Bohr had derived, and replace it with minus 1/2 alpha squared. That's because of the ke squared here. The h bars go away, and the only thing left is mc squared, 1 over n squared. So that's maybe a shortcut way of thinking about the energy of the electron quantum states in hydrogen. So remember now that the mass of the electrons are going to be at 100,000 eV. So now that we've rewritten this, I can directly use that 100,000 number because that just substitutes in for mc squared. Now I can also start with this formula up here and convert that back into kilograms, for example. Now I wouldn't have given this problem unless we had talked about this in lecture, and kind of now we have talked about it here in the review in lecture. So be aware that there's this alternate way of writing the energy states in hydrogen that uses the quantum version of the electric magnetic force constant. Okay, so when I plug these in, I'm getting different energies. That was to be expected. Changing the mass of the electron is going to change the energies. Now, the mass of the proton actually didn't show up in our formula, and here's why. As long as the mass of the proton is much, much greater than the electron, we can kind of ignore the effects from the mass of the proton. It's, to a very good approximation, we can treat the proton as if it's just sitting at rest because its mass is so large. Now, with this new alternate cosmos, or universe that we generated, the mass of the proton is still much, much larger. It's nowhere near as large as it used to be in terms of relative mass with the electron. But now, even in this example, we can continue to treat the proton as motionless. If the proton and electron mass were identical, this problem would be more complicated. Then we would have to consider the electron and the proton as both occupying the same space, and it would be more complicated to come up with the energy states for that electron-proton system. But that's not the case. We don't have to worry about it because the proton is still much more massive. So we can write down the energy values for these first four quantum states. That's what they ask us for. And I can write those down, and I can see that these are much smaller numbers. Hydrogen in this universe, the electron quantum states are negative 13.6 for the ground state. This is much smaller. And what's happening is all these others are also much smaller numbers. Now, the relative pattern looks the same. So it still looks like 1 over n squared, but instead of 13.6 here, it's 2.66. So that's the effect of changing the mass by a factor of 5. We have reduced all of the energies by a factor of 5. That's what happened. So what we can do now in part B is we can identify all the photon that could possibly be generated by all the transitions. If we're looking at the first four states, there are 1, 2, 3, 4, 5, 6 possible transitions that could occur. We don't have to look at the angular momentum states for this. We can, which actually is in chapter 39. We can do this all from chapter 37 with the Bohr model, which is a simpler, incomplete model of what's going on. And so the highest energy photons would be from 4 to 1, and by taking 2.66 and subtracting off 0.166, we get 2.49. And all the others are calculated the same way. So for all these energy photons generated in these transitions, we can go in now and find out what their wavelengths would be. So hc over energy, that's still going to work with the photons. What we're finding is there are transitions into state 1 that fall within what we currently would consider the visible spectrum. So here is the visible spectrum being produced in this hydrogen atom. These wavelengths would be off into the infrared. So the energy of the photons, wavelengths of these photons fall within the visible range. Now, we would have to ask this too. Look, if the electron has different mass, then that's going to affect every molecule in existence in this universe. And so whether or not this would continue to be the visible part of the spectrum, probably not, right? Vision would have evolved in a different fashion. Vision would have evolved with being able to pick out whatever, the sun is generating, whatever light the sun is generating, those wavelengths would also be shifted. So who knows what would happen if electron masses were changed, across the board. Maybe everything looks the same, maybe not. Maybe there are other issues that would come up. Okay, let's move on and take a look at problem 3. Now, problem 3 on this midterm looks a lot like problem 3 on the other midterm. There were 2 different midterms given different semesters, different years. And you can see with relativity, the problem that showed up was very different on the 2. Here, looking at, this is like chapter 37, looking at the Bohr model. So that's quite different. Let's see, what haven't we looked at that could show up on our midterm? Certainly we could have a Compton effect problem show up. We could have a photoelectric effect. We could have thermal radiation questions. So any of that stuff in 37 could show up. Now in problem 3, this turned out to be really similar. Let's again look at a photon, electron, proton. This time, instead of everybody having the same kinetic energy, they all have the same wavelength. So how is that going to affect things? Now, again, what I'm going to do is say the way to solve these problems is to, and they showed up on both of these exams. There could be easily something showing up on our midterm that would be similar to one of these. Now, in this one, again, the masses are going to be given values, and I wrote those down for the photon, electron, and proton. This time it says the wavelengths are all the same. So that's given as a starting point. So I wrote down 2 picometers. Now very quickly, if I know the wavelength, I can calculate the momentum. If these 3 particles, these 3 types of particles, all have the same momentum, they're gonna have the same wavelength. And so I used my general formula for calculating, for relating momentum and wavelength. And it turns out that all these particles have a momentum of 620 keV. So perfect, we got the first line filled in there. And you don't have to answer these in order. I don't know if that's the order they asked them, but I know there was a long list and they just ended up asking everything. So I just started answering things in the simplest order I could think of. And now that I've got the momentum calculated, I thought, let's do total energy. Total energy is going to be squaring the momentum, squaring the mass, adding them together and taking a square root. Now, for a photon, there is no mass, and so the energy is just Pc, and that's 620 keV. Now, the electron, remember last time we had those kinetic energies that were enormous and much larger than the mc squared for an electron. This time that's not true. This time when I'm looking at the momentum of the electron is kind of comparable to its mass. And so it's not a huge amount of momentum. And when we calculate the total energy, it's in the same order of magnitude, right? So for the electron, 511 keV of mass, 620 keV of momentum, and 803 keV of total energy. For the proton now we can see is going to be totally dominated by its mass energy. The mass on the proton is much, much larger than the momentum. When we calculate the total energy, that extra momentum barely makes a dent. So now, the column I'm concerned about is the proton column. And this time, it's not that there's too much kinetic energy or momentum. It's the momentum is so low compared with the mass, I have to watch and make sure that the relativity formulas will still work. Now, I'm going to go ahead and keep a bunch of significant figures, kind of using the same argument as I used last time there was a problem 3. And then moving on to this next row, I am going to use the kinetic energy as total energy minus mc squared and see what happens. For the photon, no big deal, because the kinetic energy will equal the total energy. So again, for the photon, it's massless. The Pc, the total energy, kinetic energy, they're all going to be the same number. When I move on to the electron, no problem. I can take that total energy and easily subtract the mass out to get the kinetic energy. On the proton, I'm a little nervous. So on the proton, I kept 9 significant figures. And when I did that, I ended up with this extra amount of total energy, and so I've assigned that as the kinetic energy. Now I put an asterisk on that, and that asterisk is telling me I'm going to come back and double check. So later on at the bottom, I'm going to come back and double check that number. But for now, I boxed it and left it there. Remember the shortcut formula for velocity, Pc over E. That's really, really handy. And so taking the V and the energy for the photon, of course, they're the same thing. I'm going to get a ratio of 1. And so the photon's going to be traveling at c, no big surprise. The electron, I can easily take the momentum divided by total. This time that's not a problem. That ratio gives me 0.772 times c. And I'm still leaving my velocities as a portion of c. Now for the proton, that ratio of 205 divided by 938,000.205, and that's in keV, that's going to give me 0.000661 times c. In fact, I'm actually a little nervous about that number. I've got to go back and double check it. So I have to remind myself to go back and just double check that number. My concern here is that the total energy is in keV, and I've written the kinetic energy in terms of EV, and so I'm a little nervous, 1/4000th. Yeah, I'm thinking that number might be off, the speed one. I got to go back and take a look in any case. All right, now for the wavelength, we already got the wavelength. For the frequency, remember, do not use c over the wavelength. It doesn't work for electrons and protons. So the frequency used here is big E over Planck's constant. And remember, I'm going to write Planck's constant on my formula sheet. There it is. I'm going to write hc on my formula sheet. There it is. 4.15 10 to the minus 18 keV seconds. So my frequency for the photon, 1.49 10 to the 20th per second, or in hertz. Same units. I can do cycles per second or hertz. Now the electron one is going to be noticeably different because of the additional mass of the electron, and so that came in at 1.93, and the proton's frequency is going to be really high because of all that mass of the proton. So in fact, that's 10 to the 23rd, which is 3 orders of magnitude larger, 3 powers of 10 larger for the frequency. Now, this problem also said if I build a couple of charge plates, generate an electric field, and accelerate these protons and electrons, what voltage would I need to use? Now the voltage is related to kinetic energies, and this time the kinetic energies are different. So in the electron case, I need something with 803,000 volts to get 803 keV. For the proton, I just need 205 volts. That's it. 205 volts is all I'm going to need to bring the proton up to enough momentum such that it has a wavelength of 2 picometers. That did not take so many volts, 205. The electron's taking 183,000 volts to do the same thing. All right, so again, practice those general formulas so that you know how to use them. Practice the shortcuts so you can use the 1240 numbers. Make sure that you've got values of Planck's constant written down in your formula sheet, not just in joules, but also in EV or keV or MeV. It just shortens the time it takes to solve some of these problems. Again, if you're not using general formulas, if you're not using the shortcut constants, maybe this is a 30 or 40 minute problem. If you have practiced using all of those techniques, it's going to be 10 minutes. And you'll be fine. I'm going to claim. All right, let's get to the last problem here. So the last problem on this midterm, this practice midterm, is kind of like the practice problem on the other one. It's another problem from chapter 38 using the Schrödinger equation. Yeah, it does say that. So a non-relativistic wave equation, which is the Schrödinger equation. And it says this time we're going to give you a potential energy function, and it's not a simple function. Before, these potential energies were usually pretty straightforward. this one I'm going to have to pay closer attention to. Now it gave us a wave function again, and the wave function it's given us is, it's a parabola. It's a parabola that's flipped upside down. So it's asking us the same kind of thing. It's saying draw some graphs of the wave functions, find some normalization constants, do some probability calculations. So let's do it. Let's see what this one looks like. So here it is. The wave function that they gave us is a, some normalization constant, times a squared minus x squared. But notice this time we do have firm boundaries. So we're back to these infinite potential regions once we go beyond little a or negative a. So out in these regions, the potential is infinitely large. Now when I square that wave function, this wave function right now is an upside down parabola, but squaring it gives me a more complicated polynomial. Now I know what's going on here is if I square this, that polynomial has to stay in the positive region. That squared polynomial is going to give me a positive number everywhere. It's got to. And so what that tells me is that those are going to be zeros. The probability goes to 0 right at the edges, but the slopes also have to go to 0 because that polynomial is getting ready to go back up again, right, on each side of that region. So, think back to all of your functional analysis chapters in your calculus classes, and the functional analysis is really handy. You can look at some of these different sorts of functions and have some idea of how to quickly represent them, quickly get kind of an estimate as to what these functions might look like. So again, wave function, probability density function. Now in part B, they want us to do normalization, so no big deal. What we can do is integrate the wave function squared. Now I use the same trick that I used on the flip side, or on the other problem 4. And that is, because this is a symmetric function, it looks like it's the ground state function, because it just has one, it doesn't have any nodes in the middle. So it's almost certainly the ground state function. In fact, it is for this potential. If I integrate half of it and set it equal to 1/2, that'll be easier. That's going to shorten things for me. It's going to make the integration go faster. So that's what I did. And then I took the a squared, and then I took all of this stuff here, the a to the 4th, 2a squared x squared plus x to the 4th. So I took that function and integrated it. So I didn't actually show it here in the integral sign, trying to conserve a little bit of paper here. But I can stare at that and imagine taking the integral at each step, and the integral comes out as a to the 4th times x minus 2 over 3 a squared to the times x to the 3rd plus 1/5 over x to the 5th. And then I'm only integrating from 0 to a, and I'm going to set the whole thing equal to just 1/2. So here's what I did. I plugged in the a squareds, and what I got were a to the 5th all the way across. So that kind of makes sense. When I'm doing these probability type calculations, everything's got to have the same units, and the units eventually have to all cancel out. So each one of these terms ended up with an a to the 5th. Everybody had the same units. And so I'm just working in terms of the coefficients. I actually got a common denominator and added those. I could have just gotten out my calculator and plugged some numbers in, but I tried doing a couple lines of algebra. And what I ended up with was the normalization constant is equal to 15 over 16 a to the 5th power square root. Now I wrote this as a squared, but we could take square roots on both sides. That's my normalization constant. So again, this problem's a little different. It's kind of interesting, I'm claiming, because it's a polynomial. And we've never really worked with polynomials before. We've always done sine functions or exponential functions. this is kind of a different sort of wave function that we're looking at. Now, what it's going to do here is, and I didn't draw it in, I guess I could have drawn this in, it's going to look at how much of the probability is between 0 and a over 2. So if I look at my graph, if we include probability from 0 all the way out to a, that would be half of the probability. Half the probability is on the right side, half the probability is on the left side, but we're only going out to a over 2, not all the way out to a. Now, it looks like most of that 50% is going to be in the region between 0 to a over 2. You can see, I guess, if my, if drawing functions is reasonably accurate here, most of that probability will be in the region closer in. So that's what we're anticipating. Now, I can use the very same integral as before, so I'm not going to set everything up again. What I'm going to do instead is start at this step right here. We're evaluating the probability between limits. And instead of going from 0 to a, I'm going to go from 0 to a over 2. And since we've already determined the normalization constant, what I can do is take the a squared and replace it with 15 over 16 a to the 5th, right? So I plug that in, and look, the a to the 5th cancel. Now, that has to happen because the constant a has units of length to it. There are units in that constant a, and the probability can't have any units. There can't be any units left. All the units are going to have to cancel out, and they just did. So that's an important check that you can make along the way. Are all the units canceling out? Yes, they did. That's a good sign. Does it guarantee we're doing everything right? No, we could have still made mistakes somewhere, but at least the units all canceled out. That's a very good sign. So I'm left with this factor of 15/16, and then I have to go in, and this time, instead of putting in 1 at each step, I have to put in 1/2 of a. So I put in 1/2 of a there, and 1/2 of a cubed, and 1/2 of a to the 5th. And what that did was it built up some pretty large denominators this time. So this time I wasn't patient enough to find a common denominator and work through all this. I just plugged those numbers in and into my calculator and calculated them. So you could go back and find out what fraction that is, because I've got a 15/16 here, and we could look for a common denominator here, and maybe it would be interesting to do that. But in any case, what that fraction, if you do that, that fraction should evaluate to 0.396. And I should say this too, unless it's a really simple fraction, you shouldn't leave the probability as a fractional number. You should convert it into a decimal so that it's easy to evaluate what's going on. So with this probability that we calculated here, what we're seeing is 39.6%, or about 40%, of the probability is between 0 and 1/2 a. And that means that if I go from 1/2 a out to a, there's an additional 10%, roughly. So if I were to divide this up into quadrants, kind of 4 equally spaced regions, the regions towards the center have 40% on each side, and those tails have 10% of the probability. So, 80% of the probability is in the central region. 20% is out on the tails. Now, we did the normalization, we did the probability calculation. Ooh, we're moving on to the more challenging part here, maybe. What they want us to do is plug this wave function in to the Schrodinger equation. So I wrote the Schrodinger equation out. I wrote in that potential function that they told me I needed to write in, and I'm a little nervous. It's a fairly complicated looking function. And then what I did was, I know I need the second derivative calculated, so I wrote down the function, first derivative, second derivative. Now in this case, I think maybe every case we've looked at, by the time we took two derivatives, we would always get the wave function back again. But this time we don't. The wave function is just a polynomial. Taking derivatives of a polynomial doesn't give me the polynomial back again. It reduces the power. And so by the time I've taken a couple derivatives of this polynomial, it's just a constant. It's minus 2 times a. So what gets plugged back in is minus 2 times a here. But here is the wave function, and here is the wave function. But I can't cancel them out because the term right here with the second derivative does not have the wave function there. Now I can cancel out the normalization constant. That's not a lot, but it's something. So I canceled out the normalization constant. I canceled out some minus signs that we had here. And then I carefully stepped through and I canceled some factors of 2 right there and said e times a squared minus x squared is equal to h bar squared over m minus h bar squared over ma squared. Now when I looked over here, I noticed that a squared minus x squared from the wave function canceled out a squared minus x squared from the potential energy function. So those did cancel and go away, and that's quite a substantial cancellation that really simplified the expression. So now the only thing I have left at this step, and remember we're solving to see if this really meets the requirements for the Schrodinger equation. What I have left is I have a constant term, EA squared, and I have an x squared term on the left side. On the right side, I have a constant term, and I have an x squared term. The only way this partial differential equation is going to be satisfied with this solution is that if the constant terms are set equal to each other. Now when we set the constant terms equal to each other, that tells us that E is equal to h bar squared over ma squared. Now the x squared terms also have a condition that needs to be met, but it turns out that it's exactly the same condition. So what it says is this, yes, this is a solution. It is the lowest energy quantum state for this potential energy function. And A can be set to anything. So there's no reason that A has to be set for any value. And that the energies that we end up with are actually positive. And those energies are going to be given by h bar squared over ma squared. Okay, so again, it's another example of using the Schrodinger equation, using a different potential energy function, using a different wave function, and showing that we can carry out normalization, we can draw graphs. So make sure that you can draw graphs of these functions and square them. And then also being able to calculate the energies for the quantum states. Okay, so we've had a couple examples of going back and looking at the practice problems that we've had, comparing the two midterms that are here. Again, a question from relativity, but from different parts of relativity. A question from the early quantum mechanics chapter, but from different parts of that chapter. A fair number of topics were covered in chapter 36 in relativity. Again, a number of disparate topics covered in chapter 37. And then this is kind of a combination of 36 and 37, and even 38, I guess. This is a combination of ideas from all three chapters. And then these wave function problems. So very likely, something involving for the Schrodinger equation, for example, either in 1 dimension or in 3 dimensions. We've looked at 3 dimensions and spent some time. That's an important example for us. or using the Schrodinger equation with different potential energy functions. Being able to take a wave function and normalize the wave function, find out how much energy that corresponds to. That's kind of a list of items from chapter 38 that are good to focus on. There should be some good examples in the homework and in the lecture examples. So that wraps up our practice set of problems from the midterms. I hope you guys are getting ready now for the midterm. I'll have office hours ongoing, so make sure if you've got questions, stop by office hours and we can take a look at those.